In this final video lecture for Chapter 15, we'll be covering synesthesia, followed by intelligence, and then we'll talk a little bit about consciousness. Synesthesia is the ability to perceive a stimulus of one sense as the sensation of a different sense, such as when a sound actually produces the sensation of color. A subset of the population experience synesthesia. It's basically the mixing of senses. It tends to run in families. The most common form is colored hearing. So when you would hear something, it would again produce the sensation of color. And most pairings are in one direction only. So for example, in colored hearing, seeing a color does not elicit the sound, but hearing a sound makes you see the color. And here is a nice brief video on synesthesia that is quite cool.
Imagine a world in which you see numbers and letters as colored, even though they're printed in black, in which music or voices trigger a swirl of moving colored shapes, in which words and names fill your mouth with unusual flavors. Jail tastes like cold, hard bacon, while Derek tastes like earwax. Welcome to synesthesia, the neurological phenomenon that couples two or more senses in 4% of the population. A synesthete might not only hear my voice, but also see it, taste it, or feel it as a physical touch. Sharing the same root with anesthesia, meaning no sensation, synesthesia means joined sensation. Having one type, such as colored hearing, gives you a 50% chance of having a second, third, or fourth type. 1 in 90 among us experience graphemes, the written elements of language like letters, numerals, and punctuation marks, as saturated with color. Some even have gender or personality. For Gail, 3 is athletic and sporty. 9 is a vain, elitist girl. By contrast, the sound units of language, or phonemes, trigger synesthetic tastes. For James, college tastes like sausage, as does message and similar words with the "age" ending. Synesthesia is a trait, like having blue eyes, rather than a disorder, because there's nothing wrong. In fact, all the extra hooks endow synesthetes with superior memories. For example, a girl runs into someone she met long ago. Let's see, she had a green name. Deezer Green. Deborah, Darby, Dorothy, Denise. Yes, her name is Denise. Once established in childhood, pairings remain fixed for life. Synesthetes inherit a biological propensity for hyperconnecting brain neurons, but then must be exposed to cultural artifacts such as calendars, food names, and alphabets. The amazing thing is that a single nucleotide change in the sequence of one's DNA alters perception. In this way, synesthesia provides a path to understanding subjective differences, how two people can see the same thing differently. Take Sean, who prefers blue-tasting foods such as milk, oranges, and spinach. The gene heightens normally occurring connections between the taste area in his frontal lobe and the color area further back. But suppose in someone else that the gene acted in non-sensory areas. You'd then have the ability to link seemingly unrelated things, which is the definition of metaphor, seeing the similar in the dissimilar. Not surprisingly, synesthesia is more common in artists who excel at making metaphors, like novelist Vladimir Nabokov, painter David Hockney, and composers Billy Joel and Lady Gaga. But why do the rest of us non-synesthetes understand metaphors like sharp cheese or sweet person? It so happens that sight, sound, and movement already map to one another so closely that even bad ventriloquists convince us that the dummy is talking. Movies likewise convince us that the sound is coming from the actors' mouths rather than surrounding speakers. So, inwardly, we're all synesthetes, outwardly unaware of the perceptual couplings happening all the time. Crosstalk in the brain is the rule, not the exception. And that sounds like a sweet deal to me.
That's a pretty cool video that covers how interconnected our senses are. And it's great to learn about at the end of this class, or towards the end of this class, because we've spent a great deal of time learning about the various senses, how the information is processed, where it travels in through the brain, and how all of the various sensory information get linked together to form representations. So in synesthesia, you have almost hyper-connected connectivity between the senses. Synesthesia has been found to be genetic, related to increased connectivity in these multimodal areas of the frontal lobes that receive input from the sensory areas. So again, these multimodal association areas, such as the frontal lobe, the temporal lobe, or the parietal lobe, the frontal lobe is the multimodal sensory area to trump all other multimodal association areas in the brain. And so it's likely that genes will influence frontal lobe connectivity to create this enhanced connection between the senses that leads to synesthesia. And here I'm going to lead into intelligence. We spend a fair amount of time being a bit worried about our intelligence because we think that it reflects a great deal about our abilities. And now that you've reached the end of this class and you have an idea of how information is represented in the brain, then I think it would be quite clear that general intelligence would be really difficult to localize in the brain. Investigations imply that cerebral connectivity and high glia-to-neuron ratio may play an important role in intelligence. And just in the way that synesthesia is this enhanced connectivity, intelligence is likely to be reflected in enhanced connectivity. Remember that the more experiences that you have, the more connections that you make. And individuals who are highly intelligent have spent a lot of time making connections, and this would be reflected in enhanced connectivity throughout their brain. We've spent a great deal of time talking about neurons, but neurons also depend upon glia to support them. Nutrients are derived from glia, structural support, so there's also some research that suggests that the glia-to-neuron ratio might also play a role in intelligence as well. In particular, in the inferior parietal cortex, this has been linked to be involved in mathematical reasoning. One of the things that I think it's really important to know about intelligence is that there are multiple forms of intelligence. This is something that we would all have lay experience with. We know that there are multiple ways that you can be smart and intelligent. Culturally, at present, linguistical and logical and mathematical reasoning tends to be associated with general intelligence tests. And so these are fostered in primary and secondary education, but there are multiple forms of intelligence, and in particular, interpersonal and interpersonal are also linked with high career success because it reflects an enhanced ability to communicate with people. So overall, these are just some of the different types of intelligence that exist. We have linguistic, musical, logical and mathematical, spatial, bodily and kinetic, and as I mentioned briefly already, intrapersonal and interpersonal. These last two have also been linked with the idea of EQ, which is emotional quotient, and that is that, again, the ability to understand your own emotions, other people's emotions, motivations, desires, thoughts. Would be very, very important for effective communication, leadership, teamwork, all things that are highly, highly important and especially prized in the corporate world. So individuals that tend to be high in intrapersonal and interpersonal skills are also thought to have this higher EQ, and that is also linked with greater success and increased happiness. There are also two types of intelligence with regards to divergent and convergent intelligence. Convergent thinking is a form of thinking that searches for a single answer to a question, such as 2 + 2 = 4. So this is what is measured in traditional intelligence tests, and people with temporal and parietal lobe lesions tend to actually perform poorly on these types of tests. Again, the temporal and parietal lobe These are also key areas that are association areas. In both the temporal and parietal lobe, those association areas, if you recall, each are part of various processing pathways for naming and identifying and interacting with objects. So information that is processed visually will travel dorsally to the parietal lobes and ventrally into the temporal lobes. And both of those are important for spatially navigating objects and identifying objects. Divergent thinking, on the other hand, is a form of thinking that searches for multiple solutions to a problem, such as how many different ways can you use a pen. People with frontal lobe lesions tend to perform poorly on these tests. Divergent thinking is linked with problem solving. Divergent thinking is also linked with critical thinking. When you think critically about a problem, then you are trying to analyze it from multiple perspectives. And again, this multiple perspectives links with multiple solutions. So convergent thinking and divergent thinking are really quite different, and they are different types of intelligence that are prized. Both of them are highly prized, but certain types of careers would require greater convergent thinking, and other types of careers would require greater divergent thinking. So while you're going through school and you are enrolling in your classes, we are trying to give you opportunities to increase both of your convergent thinking and your divergent thinking skills. Lots of the exams that we have obviously test convergent thinking, but then some of the writing reflection assignments that we have, or critical thinking assignments, writing intensive courses, or some of the oral intensive courses, those are also going to be ones that are going to require you to flex your divergent thinking skills. There's also intelligence from the inherited epigenetic aspect. So intelligence A is generally innate intellectual potential, which is highly heritable, but it cannot be measured directly. So this is basically the intellectual potential that you're born with. This is something that you inherit from family members, and this is the idea of, all right, this is how far you could possibly go, how smart you could possibly be. Intelligence B, on the other hand, is observed intelligence. This is influenced by experience and other factors in the course of development. This is actually what is measured by intelligence tests. So your observed intelligence is basically the interaction between your inherited intellectual potential and the interaction of that inherited intellectual potential with experience and other factors in the course of development. So two people can have the same high level of intelligence A, or the same high level of innate intellectual potential, but if not fostered or given appropriate opportunities during development, then they can have very, very different observed intelligence, or intelligence B. So if you are given the chance to foster your innate intellectual potential, then you will have high intelligence B, or observed intelligence. If you are not given that opportunity, then you will have lower observed intelligence. Experience may influence intelligence by increasing the number of synapses and the number of glial cells. Synaptic organization, partly directed by a person's genes, but is also greatly affected by experience. So as we've talked about numerous times throughout this course, genes and experience interact to create synaptic pathways, to result in synaptic pruning, to increase dendritic fields, to create neurogenesis, and the constant interaction between gene and experience, this contributes to intelligence. And we're going to end the chapter talking about consciousness. Why is it that we're conscious? We think of consciousness as this higher level awareness that is unique to humans. So we're very much concerned about what it is that then makes someone or something conscious. When we talk about consciousness here in this chapter, we're not going to be talking about sort of the metaphysical aspect of consciousness. We're going to be really talking about what consciousness is from a basic biological level. In terms of the basic biological definition of consciousness, this is a level of responsiveness of the mind to impressions made by the senses. So this is really closer to the medical definition in the sense that you are conscious if you are, again, responding to your environment, but consciousness is sort of this idea of level of responsiveness of the mind. So highly conscious individuals are going to be highly aware of their continual interaction with the environment. And evolutionarily speaking, consciousness would provide an incredible adaptive advantage, because if you have an awareness of how you are responding to the environment, then this would significantly enhance your ability to learn and then improve over time. And not just learn and improve over time automatically, but learn and improve over time deliberately and with intent. And this deliberateness and with intent over hundreds and thousands of years is what would give rise to a lot of the complex interpersonal interactions and overall existence that we have with regards to culture, language, and our highly social and mental world. So consciousness emerges from neural circuits rather than from individual neurons. Consciousness is really best represented as being more than the sum of its parts. The greater the degree of complexity in neural circuitry, the greater the degree of consciousness. So, what is the basic neural basis of consciousness? There are conditions in which people can process information without being aware of that information. And we've talked about a couple of them in this course. Blindsight, which we haven't talked about. Visual agnosia, which the chapters have touched on. Visual neglect, which we've talked about. And amnesia, which we've also talked about. There are also conditions in which people have conscious awareness of events that are not actually present. This would be phantom limbs, and this would also be hallucinations. So how do we then put these two pieces together? So we have conditions in which people process information that they're not actually aware of. And then we also have conditions in which people have conscious awareness of events that are not actually present. These two ends of the spectrum suggest that consciousness is likely a product of all cortical areas and their connections and their cognitive operations. So the representation of a visual object is likely distributed over many parts of the brain, and parts of this neural circuit must produce awareness of the visual object. So then if you have disruptions in that circuit, then you're going to have disruptions in being aware of that visual object. Likewise, if this visual representation is distributed over many areas and this visual representation gets activated in one area, then that would extend to the other areas even if that visual information might not be physically present in the environment, as such would occur with hallucinations. So consciousness really is putting all of these pieces together, all of the intricate neural processing that we have, being aware of how we are processing information. And in being aware of how we're processing information, we can also change how we interact with the environment. And all of this is dependent upon the interconnectivity of the neurons in our brain. And this ends chapter 15.